I am the PI of the Venus Flagship mission Planetary Decadal study working with Pat Beecham, who is there. Steve Kane and Shannon Curry are also in your audience. And join a host of, actually, if you could advance, Noam, next slide. Yes, are part of a wonderful science team that have been working for over a year now, thinking through what we would like to do at Venus with a flagship class mission. So this is a list of the science team. We're working with Goddard Space Flight Center to design the mission. And we'd also like to thank, there's a host of generous colleagues who have just been talking to us about what they have been doing, which have made this study possible. So the next slide describes a little bit about the Planetary Decadal study process. We had our last decadal in 2013, and so the next one is to start for the 2023-2032. And so in the last decadal, you may remember, NASA requested, and the panelists requested studies be done during the time of the decadal, during the survey itself, where they worked with teams at Goddard, JPL, and APL to try to design missions that could be costed. And this was a response to the decadal before that, when people were worried about the fact that although we said we wanted a lot of science, it's really important to know how much it costs in order to make decisions about what missions should fly. So we did 32 studies were commissioned in this process last time. They're all available on the web, actually, if you want to go see them. For this decadal, there was a decadal midterm that decided that it might be better if these studies were performed prior to the decadal survey starting. So NASA put out a call. 11 studies were selected across the solar system. We are all teamed with NASA centers, and we are all preparing to these mission studies for June 30th. So one of the things I'm asking of you as a community, exoplanet folks, is I think that the Venus Flagship study is another opportunity to input exoplanet science into the decadal because of the importance of Venus as for exoplanet science. I'll try to make that case along with others. The next slide shows that the schedule for what we're doing, it's very fast. The study was just initiated. We have received lots and lots of input from the community, and we will have 2 engineering runs at Goddard Space Flight Center to try to develop the mission. In March, the day before LPSC starts, Sunday, there will be interim reporting. All of the planetary decadal studies will talk, so you're all invited to that. The final report's due at the end of June, and then for the white paper process, we are asked to submit white papers, all of you, if you're interested, again, by July, when the panel's set to begin. Okay, next slide. So the Venus Flagship, our science team came to a consensus that we would like to use the flagship class to assess the habitability of Venus. And this is distilled into 3 goals: the history of volatiles and liquid water on Venus, and determine if it was habitable, to measure the composition and infer the climatological history of the surface of Venus and present-day couplings between the surface and atmosphere, and to look at the geologic history of Venus and whether Venus is active today. So the next slide shows part of the reason why we are able to turn our focus to habitability. It's this idea at the upper left that in the beginning, there were 3 terrestrial planets with oceans in our solar system, and they've all evolved on different paths. The graphic on the right is actually a very nice paper spearheaded by Darby Dyer that came out in Scientific American. It shows planet formation, 4 billion years is at the top, today is at the bottom, and the evolution of volcanism in red, the persistence of volcanism, and the persistence of liquid water in blue. And the data from spacecraft and from modeling that Mike Way is doing, for example, have done 2 things. They've really helped us appreciate that Venus may be geologically active today, based on observations from the Venus Express spacecraft. And the new climate models that are coming out that Mike is doing are showing us that water may have persisted on Venus for several billion years, which is longer than we had thought previously. So this is coupled with the fact that Venus Express has observed the surface at 1 micron, which is a window down to the surface. And what you see on the lower left is a 1 micron image of Alpha Regio Tesera, a deformed highland on Venus. The difference in the color can be related to iron content. And these rocks in the Tesera, which are the oldest rocks on Venus, and I've pointed out the crater age for the Tesera, overlap potentially a time when water could have been present on the surface of Venus. And the lower iron content inferred from this 1 micron signature, at least in my mind, supports the fact that they could have more siliceous magma, could be comprised of more siliceous phases, and may be felsic or granitic. So if they were, that would also point to having water, a lot of water, and plate recycling in order to get that water back into the mantle. So the next slide shows also the work of Steve Kane and others that are pointing to the fact that many of the exoplanets that you all are seeing are actually exovenuses. So the next slide shows, and this is, sorry, but this is just my, we also need to explore Venus, and there are 3 missions in contention and discovery right now that we should hear about anytime to Venus. There's a Envision you've heard about going to be, is in contention for ESA. This is a woefully unexplored planet, and it has a lot to tell. Next slide, please. Okay, so the overview of our mission is that we will attempt to launch several assets that will be performing synergistic measurements of the Venusian system in order to track the presence and fate of volatiles from mantle to exosphere. This consists of 1 orbiter, 2 orbiting small sats, 1 short-lived lander, like a Venera lander, and by short-lived I mean hours, a balloon, and a long-lived lander, which could be a LISSI, I'll describe it to you in a moment, that could last, built out of high-temperature electronics, could last for 60 days. We're trying to have this mission come out to about a $2 billion cost cap in order to make it more feasible. Especially in the current climate where we have so many other spacecraft going to Mars and Europa. So the next slide, I will begin to this is just to show you that Goddard has started working on this, and it fits on a rocket. But just to show you how we're envisioning the balloon, lander, small sats, which are carried on an ESPA ring, and the orbiter. Next slide, please. So I'm going to kind of quickly go through the instrumentation and the assets, and then at the end, just I want to come together in summary. So Enroute, the plan is to release 2 small sats with an ESPA ring. Shannon is leading this effort. On the left, for each of these slides, you're going to see our instrumentation. Green is our must-haves. Not green is we'd like to have. And the science here is, of course, is to understand the evolution of the Venus atmosphere by measuring the interaction of the atmosphere with the solar wind over the entire mission. So to have 2 small sats opposite each other, looking at the system through solar cycle 25, and which will be an improvement because of the instrumentation and the orbits on anything that has been done before. The other thing that we're learning is that this also significantly aids in the tracking of the balloon and the communications with the landed assets, which we are trying to take into account, but should allow for more flexibility with getting, we should be able to get more data back. The next slide is Upon arrival, we will deploy the balloon. The science of the balloon is to understand the composition and the nature of cloud particles, and this will be measured with mass spectrometers, nephelometers. And there are a couple other instruments that can also assess things that we haven't assessed before. Fluorimeter to look for chemistry necessary for biology. This is all in the gondola. Measurements of the magnetic fields at this altitude, and also a tether to measure pressure differences that could be that are in the infrasound range. And there's been a fair amount of work that has shown that you can detect seismic activity in the Venus atmosphere because of its thickness as pressure waves. And so we're hoping that a pressure sensor in this range could help at that frequency, could perhaps detect some Venus quakes over the minimum 30-day lifetime of this balloon. The next slide. After the deployment of the balloon, we seek to insert the orbiter, which at this point is carrying the landed package. And the orbiter would carry a radar for geologic mapping, a near-infrared imager, which would do what Virtus did on Venus Express, the data I showed you for Alpha. Virtus has been able to look at the 1 micron emission from the southern hemisphere of Venus, which is related to mineralogy, as I mentioned, and we would certainly want to be able to improve the that global mapping for to try to assess global mineralogy. It would be equipped with some of the small sat electric particles and fields. And the idea is to have 2 types of orbits. The first would be to have a landing site campaign where the orbiter is in an high elliptical orbit, actually, that can image the surface, potential landing sites at the surface at periapsis, and then have a high apoapsis and able to be able to maneuver and also look at the lander. So it would be carrying the lander for about a Venus day. After the lander was deployed, it would enter into a mapping. It would aerobrake down and enter into a mapping campaign. The details of which we have to consider what is selected in Discovery and by ESA, and we certainly hope that Venus missions are selected. The next slide is what you see is the Tesera terrain in yellow and some nominal landing sites that Goddard is looking to try to target for landing in the Tesera. And the next slide shows that en route to the Tesera, there will be several instruments, the mass spectrometer, tunable laser spectrometer, imaging pressure and temperature to measure a much needed profile down to the surface, isotopes and just the composition. I just put a quote here for the justification. We don't know anything about the lower atmosphere, says a colleague of ours who shall remain nameless. So it's a very important measurement for all kinds of things like climate models. The next slide, please.
Just a minute or 2 left, okay?
I'm sorry?
Just a minute or 2 left.
Oh, okay. Finally, sorry, 2 slides left. We have a ambitious lander where we seek to both ingest materials into the vessel and also look at the rocks using Raman libs, so that in the end we would have 3 instruments that would separately look at chemistry, 2 instruments that would look at mineralogy, and the Raman, which adds redundancy, and that the Raman libs give some sense of mobility, as much as we can on Venus. So if we can just go to my last slide, Noam. I'm sorry, I'm over time. Last slide, skip this. That's all my nice squiggles. Next slide, please. Okay, so I drew this yesterday because I'm in my hotel room, but the basic question for you guys is, what do you want to know about an exoplanet? And what I've garnered from the discussions that I've heard today and just from what I know is I tried to draw it on this slide. You have a G star of known composition. You want to relate that to the solid body. We want to understand oxidation state, the loss of oxygen, all of these cycles. We have the opportunity to look at ancient Venus in the Tesera and modern Venus in the plains. We want to know activity. So what I would ask is that if you have specific measurements that we could do with the instrument suite that we described, that we could, I would be happy to talk to them and talk to you about them so that we can ingest that into the study, even as an appendix to talk about what could be done with exoplanet science. And as Steve Kane says, studying exoplanets is not going to be easier than studying Venus because it's right here. Okay, thanks all.
Thanks, Marty.